Hey guys, welcome back. In an earlier video, we learned about linear regression. Today, in this video, we're going to learn about something called binary classification. If you don't know what binary classification is, let me tell it to you now. So let's first cover what is binary classification and why should you use it. Well, the thing is, binary classification is used for situations where you have a yes or no data set. So for example, emails that are marked as spam or not spam, or if you give an image to your neural network and the neural network decides if the image contains a hot dog or not a hot dog. Similarly, in the real world, credit card companies use machine learning or binary classification to find out if a purchase is valid or fraudulent. Now that you know what binary classification is and when is it used, let's head on to Google Colab where we can write some code. So as a first step, let's create a dataset. So there's a function from scikit-learn called makeCircles. So looking at the documentation, it just makes a bunch of circles and it only serves as a toy dataset for clustering and classification algorithms. So let's use this function. So first I go import sklearn, import sklearn.datasets, import makeCircles, and here we're gonna have s, not sx, comma y equals makeCircles. So the first parameter is the number of samples. So I'm going to create a variable for that. So n samples equals 1000. Let's make 1000 samples. So n underscore samples, comma, and then we have something called noise. So just add some noise to the data set. So add noise as 0.02. So some noise, and yeah, this looks fine. So basically what this function will do is it will create a data set where our x will be the generated samples, so basically a bunch of numbers, and y is going to be our label. So in this case, our label is going to be either 0 or a 1. In other words, this is perfect for binary classification. This is because a 0 can be a no and a 1 can be a yes for our binary classification algorithm. But you'll know what I mean in just a second. So anyways, let's run this code. Okay, so I made an error here, of course, so it's from, and now we shouldn't have any error. Okay, so far so good. Now what I can do here, let's check what our x and y variables look like. So I go print x, and I'll print only the first 5 elements of x, and I'm going to do the same for y. Okay, so as you can see, for every 2 numbers of x, we have 1 value of y. As stated earlier, y can either be a 1 or a 0. So moving on, for example, we have 2 numbers here again for our x values, and for our y values, we have another 1. Another better way to visualize this is we can use a pandas data frame. So here I go import pandas as pd, and then circles, so circles df, let's call it pd.dataframe. So it's pd, not df. And then here let's do x1. So x1 will be the first column of our x array. So here I'm getting all of the items within this x array and only getting the first column, comma, let's do the same for x2. So x, and then this time it's going to be the second column. So this one, so 1, comma, and then let's do for y. So in this case, it's going to be label. So our intended output, and we have only 1 value. So just y. That's it. And then at the end, I'm going to go circles df.head. Let's run it and see what happens. Okay, so we have this output. So it's a bit clearer to visualize here. So as you can see, for every 2 x values, we have 1 y value. Now, obviously, I don't really know the pattern here. I don't really know what kind of x values we need for a y value to be 0, or what kind of x values we need for a y value to be 1. But this is not our problem. This is something PyTorch will do for us. So anyways, let's move on. I'll create a new code snippet, and let's now find a better way to visualize our data. Let's now plot this data set. So import matplotlib.pyplot.splt. then plt.scatter. So our x is going to be the first column and y is going to be the second column of x. And then we can set the color markers to y and then cmap plt, so the color map, and let's find one, .rdy. So this color map looks fine to me. And then let's run it. Okay, so this is our data set now visualized. So as you can see, some of the X values have a label of 1 or a 0 depending on the color. And one more thing to remember is that our data set here does not have a linear relationship. So this disqualifies our data set to be used for linear regression. Just had to put it out there. Okay, this time let's move on to creating our test split. So here I go from sklearn.model_selection, import train test split. So I want to split my data set into train and test data sets. And then I go x_train, x_test, so we have autocomplete. Looks like it went away. y_train, y_test. So I declare my data sets equals train test split, and then I specify my data set. So I want to split my x and y data set. So x, y, and then test size. So normally people use a 80-20 size for our test split. So basically 20% of our data set is reserved for test data set. And then we want a random state. So let's set random state to 30 and then let's run it. Okay, so it ran. Let's check what X train looks like. So I'll get the first 5 items and let's check what the Y train looks like. Okay, it looks like this. It's fine so far, and then I can get the length X train and get the length of X test. So it's 800, 200. Yeah, that checks out. Let's now move on to creating a neural network. So here I'm going to put the heading, building a model. So just for organization purposes. And then here I'm going to go from torch, import NN. So for my neural network. And then let's build the class for a neural network. So class circle model, because we have circles here. And let's give it versions. So I want to create multiple iterations of my neural network. So here let's do model v0 and then nn.module. So this time let's create our layers. So in our video for linear regression, we just use one linear layer. But the thing is, our dataset looks a bit more complex. So generally here, according to Google and multiple sources, more layers generally allow a better neural network. However, in some cases, they don't really guarantee a better model. Let's experiment. Instead of one linear layer, we can use 2 linear layers. Maybe that will work out for us. So here I go self.layer_1 equals nn.linear, and then here it will have in_features. So here for our input we have 2 numbers, so 2 inputs, so to speak. So in features is going to be 2, and then we can have out features. So let's leave it here for a second. So I'll build another layer, layer 2, nn.linear. So in features, and one thing is, what do we want in features here and what do we want out features for layer 1? Well, the thing is that out features for the first layer should be equal to the in features of the second layer. This is because layers in general have to hand off data to each other. So if we have out features, for example, equals to 5, then layer 2 will expect 5 inputs, and then out features here. So in our case, since we have 1 output, so out features should be 1. And then let's define our forward function. So def forward, so self comma x, so my input, and then return self.layer2. So I perform my computation, and then self.layer_1. That's it. As a matter of fact, it's better to refactor our code a little bit. So here, instead of manually declaring layer 1 and layer 2, we can do self.toLinear layers equals nn.sequential, and then here we can define our layers. It's basically the same thing. So I just copy this here, comma, and copy this. That's it. So basically this and these 2 lines are basically the same thing. So I'll remove this. And then for my forward function, instead of this code, I go return self.toLinear layers and then just pass x. That's it. So I remove this line and let's run it. Okay, so no error so far. So now let's create an instance of our circle model. So here I go model underscore 0 equals circle model v0, and then I can just do a print, or I just want to see how my model looks like. Okay, yeah, that checks out. 2 linear layers with these features, and let's check the parameters. So I go model underscore 0 dot state dict. So yeah, as you can see, this model is starting out with completely random numbers, and obviously while training, these parameters will adjust themselves to get our desired result. So anyways, let's try performing some inference on our untrained model. So here I go with torch.inference mode, and then here we go untrained result equals model underscore 0 and then x test. So let's do it on a test dataset. So let me fix my indentation. It should go back, and then I import torch, and then at the end I can get what the untrained result looks like. So it's going to be a very big array, so I'll just get the first 5 elements, or it's better to get the first 10 elements. So basically I just want to see how the model performs without being trained. So let's run it. Okay, here as you can see we have the following output. We have an error. It's more or less a data type error. So our model here expects an array of type tensor. However, our data set here is of type numpy array. So let's try to fix it. So I scroll all the way up around here, and here we can write some code to convert our data set into tensor arrays. So here for the first part, I'll convert the x numpy array into torch, and then at the end I'll convert it into a float, since this is what my neural network likes and this is what PyTorch really plays well with. And then I'll do the same for y. So y equals torch from numpy y, and then do the same conversion to float. So let's run this code again. So now our x and y data sets have been converted, and let's see if this works. Yeah, this works fine. And now if I run this code, hopefully we don't have an error. So as you can see, we have the following results. The thing is, after we ran this code, notice we got a bunch of float values, and scrolling up, our labels or our desired outputs is either a 1 or a 0. Basically, we want whole numbers here. So what's happening here? Why aren't we getting whole numbers? Well, the thing is, these numbers are actually raw outputs, so they haven't been run through an activation function. So here we would need to process these raw numbers. In the world of PyTorch, these raw numbers are called Logits. Now some of you might have a question about what Logits are, and I'll explain them to you now. So Logits, what are they really? So as stated earlier, Logits are raw numbers, so raw output from the neural network that were not passed through an activation function. And since these are raw numbers, we need to interpret them as probabilities. We need to convert them into proper probabilities. Now the question is, how do we convert them into probabilities? Well, luckily there's a function called Sigmoid. So Sigmoid basically takes your input, it takes your logit, and it converts it into a probability or a prediction. So this will help us out. In simpler words, our Sigmoid function will take a logit and then it will return a probability for that logit. So now that you have a brief overview of what logits and sigmoid functions are, let's continue to writing some more code. So here, instead of printing the untrained result, I can print the torch.sigmoid. So convert these logits into probabilities. So I'll copy this like so, and let's run it. So as you can see, each of our logit, so our logit number is converted into a prediction. So let's write a rule here for each of our prediction. So let's say if our prediction is more than 0.5, then the label should be 1. Otherwise, if the prediction is less than 0.5, then the label should be 0. So now with that being said, let's now create our loss function. So for linear regression, we use something called L1 loss. But for binary classification, we use something called binary cross entropy. So luckily, PyTorch provides us with a loss function already defined. It's called BCE with logits loss. So let's make one like so. So loss underscore fn equals nn.bce with Logits loss. And then I'm going to create my optimizer. So optimizer equals torch.optim.sgd. And then my params, so model underscore 0 dot parameters. And then my learning rate, so I'll set it to 0.01. So I'm going to make a heading here, setup plus function and optimizer. Okay, so let's run this code. Okay, so now with no errors, let's now write some code. I want to build an accuracy function. Basically, I want to check what percentage of my data set is my model getting right. So let's try to build the premise for now for our accuracy function. So I create a tensor, so torch.tensor, and it will have these values, and then b torch.tensor, and let's do 1 for 6. And let's check how many items of these tensors are equal to each other. To do so, I'll do torch.equals a comma b. So one item is true, so 1 here is equal, and the rest of them are false, so 4 and 2 and 6 and 3. Okay, so now what we can do here, we can do something called dot sum, so it can check how many items are true. So one item is true, and then I want the number from this tensor, so dot item. Okay, so now we have basically the premise of this accuracy function. Actually, you know what? We can even assign this a number. So let's do correct equals, and then correct slash length of a, I'll wrap it in brackets, multiplied by 100. And then it will give us the percentage of how many items are correct. So 33% of our items are correct. Let's add another number. So 100 here, and then 100 here. Okay, so 50. So basically 2 items out of 4 are equal. Okay, so now let's actually build our accuracy function. So here I go def accuracy fn and y predictions, comma, y true. So the correct values and the predictions from the model. So I'll just copy this code, and this time it's y predictions, y true. So basically we want to check how many items are equal, and then we return the percentage. So accuracy equals correct slash length of y predictions multiplied by 100. So get the percentage, and then I return the accuracy. So let's run it. Okay, so no errors. Let's try to test this function. So I go accuracy underscore fn and then a and b. So let's see what it gives us. 50. So basically our function is now performing just as expected. Let's now write some code to actually train our model. So I create a text snippet, and with the heading train model. So here let's write some explanation. Here let's write we need to go from raw logits to prediction probabilities to labels, so either a 1 or a 0. So our model output will be raw logits, and we saw this earlier. There were raw logits, and then we can convert these logits into prediction probabilities by passing them into the Sigmoid function. Again, we did this earlier using the torch.sigmoid function, and then we can convert these model predictions to labels by rounding them. So we have done 2 of these points, and let's do this one. So I'll scroll up and I'll copy this code. Let's paste it here. Basically, it's all more or less the same thing. Let's now try to round these predictions. So we have autocomplete. So let's make this code a bit easier to read. So I go result equals this value, and then Sigmoid. Actually, it's better to convert it into, or rename this variable into y predictions equals, then let me remove these brackets. And then I go y prediction labels torch dot round y predictions. That's it. So let me fix my code, and then let's print all of this code. Sorry, not this code, these variables. So result, and then prediction and prediction labels. Let's see what happens. So when I run this code here, as you can see, we now have our prediction probabilities, and all of them have been rounded. So whatever's below 0.5 has been converted to 0, and what's above 0.5 has been converted to 1. One more thing is that notice that we have this extra dimension, so we may need to use the squeeze function. So this is something we need to keep in mind while training our model. Let's now write our training loop. So epochs equals 1000. Again, if you want to learn about the training loop, refer to my video on linear regression. But anyways, for epoch in range epochs, and then I train my model. So model underscore 0 dot train, and then y logits model underscore 0 x train, and then we have an extra dimension. So let's squeeze it, and then y predictions, or it's better to call it y labels since we're rounding it. So y labels, actually y labels, it's not a good name, so y thread is better. And then let's use our loss function. So loss equals loss fn y logits comma y train. So some of you might be thinking, why not use the torch.sigmoid function here? Our model is learning from the predictions, not the logits, right? Well, the thing is, our loss function, which is BCE with logits loss, already includes a sigmoid layer. So here, passing in another sigmoid is really unnecessary, and it will result in problems. So yeah, that's why we're not using a sigmoid function within our loss function. And then accuracy, so accuracy fn, and then y predictions, so y pred comma, and then y true, so our desired output, and then optimizer.0 grad, so 0 out the gradient, loss.backward, and then optimizer.step. And then let's use our test dataset. So I go model underscore 0.eval, so turn on evaluation mode. So with torch.inference mode, model underscore 0 x test.squeeze, and then we get the prediction probabilities for our test dataset, and then let's print it out. So I go if epoch, so I want to print out the results after every 10 epochs. So here I go after every 10 epochs, I go print f epoch, and then epoch loss. So let's take this loss, accuracy. So it's accuracy, and then test loss. Looks like I did not define my test loss. So test underscore loss equals loss fn, test logits and y test. Then I do the same for my accuracy. So test accuracy is equals accuracy function. So y predictions is my test predictions, and then the true result. Okay, so anyways, test loss, test accuracy, so test accuracy. And since accuracy is in terms of percentages, so I go percentage here and percentage here. Okay, so a lot of code written. Let's see what happens when we run this. Okay, so now with my code ran, the output is a bit messy, but let's look at what's really happening. So the general trend here is that while yes, our loss is getting lower, notice that our test accuracy percentage is 50%. So yeah, 50% and 50% here. Not exactly 50%, but nearly 50%. This is more or less a coin flip. Our model as it stands currently has a 50% accuracy. Here, I would say that the accuracy is really, really low. So we learned from an earlier video that training our model for longer might result in more accuracy. Let's try running the training code once again. Okay, it's still 51%. And as a matter of fact, our test accuracy has lowered. Let's run it again. Maybe it works. Third time's the charm. So as you can see, our test accuracy is still 46%, and the accuracy from the trained dataset is 51%. So something's wrong here. Let's try to fix it. So earlier we discussed that generally giving our network more layers or adding depth to our network can generally improve performance, but obviously in some cases it does not improve performance. So let's try experimenting here. Let's try giving our network one more layer. So I'll scroll up and let's find where our neural network was defined here, and then I'll copy this. Let's scroll down. I'll add a text snippet adding depth to neural network, and let's paste our code. So this time it's circle model v1, and let's add another layer. So nn.linear in features. So I'll change the out features to 5, in features to 5, and then out features to 1. So it's linear. Looks like I messed up the spelling. And then model underscore 1 equals circle model v1. So let's run this code and let's run this code. So now our model 1 is defined, and then let's run our training loop on model 1. So maybe let's see what happens. So I'll copy this code and we paste it here. Instead of model 0, it's going to be model 1 here, model 1 here, and then model 1 here, model 1 here. So yeah, it looks fine. Okay, so now let's run this code and let's see if adding one more layer results in better performance. Okay, so a few seconds later, my code has run, and scrolling down, notice that my accuracy is still 51%. So then what's wrong here? I mean, we've done everything correctly. We've given our network more layers, and we've also trained our model for longer. Furthermore, we also set the number of epochs to be a really large number. So what are we doing wrong? So let's try to find out what we're doing wrong. So let me find my plot of my data set. So let's scroll up around here. So notice that our data set is non-linear, and we're using a linear relationship to model or fit this data set. And obviously we can see that a non-linear data set cannot really be modeled by a linear layer or a couple of linear layers. So luckily PyTorch provides us a ReLU layer or a ReLU function, and it's a non-linear function. So let's try to experiment. Let's see what happens if we use a non-linear function or a non-linear layer on our data set. So I'll scroll down and let's copy this code. So let's create another neural network. Let's call it circle model v2. Let me add a heading, adding non-linearity. So the question is, where do we add our ReLU layer? Like where in this row or where in this sequential layer? The general answer is that we added between our input layers. So here we added an n.ReLU, comma, here as well, an n.ReLU. So yeah, between our input layers. So now let's test it out. So I create another model, model underscore 2 equals circle model v2, and let's run these code snippets. And then let's use the training loop once again. So I'll copy all of this code, paste it here. So model underscore 2, let's replace all these instances of our model 1. So here, here, and yeah, this looks fine. So let's run this code and see what happens. Okay, so here we have the following results. My code should have worked. We should have a higher accuracy, but I found out that I made a critical error. I made a coding error. So our optimizer that we've been using so far has been linked to model underscore 0. So I might need to change some of the code here. So for example, for model v1, I will redefine my loss function. Actually, not my loss function, my optimizer. So yeah, so for model 1.parameters, and let's run it. More or less, I expect the code or the results to be the same. So yeah, the results are same. And for model 3, so for my non-linear model or the model with a non-linear layer, so here I go optimizer equals torch.optim.sgd and then model 3.parameters, and then let's run the training loop once again. So hopefully this time I should have a higher accuracy. All right, so running my training loop a couple of times, we have a higher accuracy than before. That's amazing to see. Our model is more accurate than the previous models. So just to speed up things a little bit here, I will change the epoch interval to 100 or the logging interval, and let's change the number of epochs to 10,000, and then let's run it again. All right, so now that my code has ran, notice my accuracy this time is 100%. That's amazing. So let's try to perform some inference. So I'll copy this code for inference. Let's fix my code here or my indentation, and then instead of xtest, it's going to be xtrain. Let's do model logits, model pred. Let's pass model logits here. Let's change this to model loss, and then yeah, change the variable names basically. So y test is here, and then model pred goes here. Actually, I don't need this code. I just need the predictions. So let's get the first 5 predictions. Let's print it out. And let's do the same for my y test. So let's see how it looks like. Whoops, so it's not xtrain, it's xtest. So let's run it. Great. So as you can see, the first 5 values are matching up perfectly. Let's do an accuracy function. So accuracy function. And then my y predictions is gonna be model pred, comma, and then y true. So the actual output is y test. So I expect it to be 100%. Amazing. That makes me really happy. So what did we learn today? In this video, we learned about the basics of binary classification. Furthermore, we also learned about non-linearity and how non-linearity is great suited for more complex datasets. And yeah, that's it for today. If you guys have any questions, let me know within the comment section below. I'm open to any ideas or any suggestions or any opinions. Till then, see you later and bye bye.